Okay, welcome to ESMARConf2022 and this workshop on structural equation modeling. This workshop is being live streamed to YouTube and has a group of participants taking part live. Welcome to all of you here and all of you watching on YouTube. If you are watching via YouTube and have a question for our presenter, please reply to the tweet in the ES Hackathon Twitter feed, and we'll try to reply to those as soon as possible. Also, we'd like to draw your attention to our code of conduct, which is available on the website, which is esmaconf.github.io. So it's with great pleasure that I introduce you to Arindam Basu, who's at the University of Canterbury in New Zealand, and he's going to talk to us today about structural equation modeling. Really looking forward to this. Over to you, Arindam.
Thank you. Thank you, Matt. Hello and welcome, everyone. My name is Arindam Basu, and I am from the University of Canterbury. I am an associate professor of environmental health. And today we are going to discuss and see a workshop about meta-analysis, but we will be using structural equation modeling. So let me share my screen, and let's go over some of the initial things that we will be doing in this workshop. So I am going to share my screen. So Matt, is it okay that I take off the banner and then put my screen in?
Yeah, that's fine.
Yeah, with your permission, let me do that. And so I will be sharing this. I'll share sound, optimize for video clip. If there's any, share it. Okay. Can you see my screen? If you can, it says that participants can see my screen.
Yeah, we can see your screen now. It's yeah.
And I will turn on a slideshow to start with, so that it becomes easy for you. You can exit the full screen, or you can do however you like. I think I'll probably have to exit the full screen at some point. So one of the things that's quite important for us in doing the structural equation modeling, workshopping this is that this is a fully interactive workshop, which means that please feel free to interrupt me at any time that you would like to do, and ask questions, post your observations and things like that. It's a fully interactive workshop in that sense. I don't want to be the talking head all the time. Second thing that I want to emphasize in this workshop is that we will not be able to cover everything, because both structural equation modeling and meta-analysis are kind of semester-long courses that people have been doing. And, I mean, you can have multiple semesters of structural equation modeling and meta-analysis going forward. So I don't want to compress everything also in a 2-hour workshop. So I will probably be touching only the surface and the prelims of it. So you're more than welcome to continue this conversation even after this workshop if you're interested. In the front screen, you can see my email address, arindam.basu@canterbury.ac.nz. I am also active on Twitter. It's Basu. And those are the two main channels in which you can come in contact with me, ask me questions, and we can continue this conversation. And for this workshop, I have also got a GitHub repository set up, which I will give out in a bit. So to go over the plan of the workshop is going to be something like this, that I'm going to talk about a meta-analysis and some of the key things about meta-analysis that makes it particularly useful for structural equation modeling to be segued into it, and emphasize that meta-analysis essentially is a multi-level modeling exercise. Then we're going to talk a little bit about what meta-analysis looks like to the eye of structural equation modeling and structural equation models. And for this workshop, we will be using an easy to use, I say easy to use, but difficult to understand R module and R program called metaSEM, which is written by Mike Cheng. And Mike Cheng has done phenomenal work, including writing a book and a very readable paper in the Journal of Statistical Software on metaSEM. I encourage you to look it up. The other name that comes to mind in terms of conducting meta-analysis with structural equation modeling is Matthias Harrer. He has already spoken in this conference. It's a fantastic web page. If you can have a time, go take a look at it. It's called Demeter, and we'll introduce that to here as well. I will be speaking mostly and only about univariate and multivariate meta-analysis in this workshop. However, applications of structural equation models in meta-analysis extends beyond this. So you can do things like synthesize entire correlation matrices and then use structural equation modeling to analyze them. And the other thing that I probably will have not time to touch is there are some other details and some other things of structural equation modeling and meta-analysis that are quite useful that I will not be able to touch in this workshop. And of course, as you know, you're free to ask any questions, discussions, and I will be keeping an eye on the chat for any questions, just in case. If you have got any questions, please feel free to draw my attention and ask questions using your hand symbol or using a thumbs, however you may feel comfortable in asking those questions. Now, what happens is, because this is a workshop, and what I would also set the scene and tone here in putting together a Google Docs document. And what I'm going to do is the Google Docs document lives here, but I'm going to leave the Google Docs link in the chat box. So let me see how we can do that. So if I take the Google Docs, this is the Google Docs document. Can you see my Google Docs document? If you can you please give a thumbs up or something? I will also post it in the chat, just in case you wanted to connect to it. Now, what happens in the Google Docs document is this, that I have put together the list of your attendees. So if you can please leave your name, your email address, and your Twitter handle if you have one, that would be really useful. And then there are a couple of questions. Don't answer these questions yet. We will get to these questions in due time. But for the time being, if you can kindly put your name, your email address, and your Twitter handle, that would be really useful, because we can continue this conversation afterwards once this workshop is over. So maybe perhaps we can wait for a few minutes while you can do that, and see if you have got any questions going forward. So what questions do you have before we get started with the first things? So maybe we can give people some time to fill in their email addresses and Twitter handles, and then we could do that. Okay. Yeah. So we'll start in a minute. Let me finish you, and if there are any other questions, please ask me. Okay. Now that's number one. the second requirement for this workshop is this, that when you signed up, I kind of, Matt and Neil sent you an email asking you to, if you can kindly download an RStudio instance. So if you could, if you have got an RStudio account already set up, can you give me a thumbs up to say that that's the case? If you could put it there, thank you very much. And there are quite a few thumbs up going up now, informing that, okay, you have either an access to an RStudio or have got an account in RStudio Cloud. That's really useful, because that really will help me to show you some work which you can then reproduce in RStudio. And I will be moving back and forth in between my RStudio instance and this presentation, so that you will have a sense of what actually happens in the real life as we go ahead with meta-analysis and using structural equation modeling. The other thing that's quite useful for this workshop is a structural equation modeling package called Lavan. Lavan is actually a very useful and easy structural equation modeling package, but unfortunately, at this stage, Lavan is not very well suited to do meta-analysis. The only thing that you can probably do is a fixed effects univariate meta-analysis. But as we will be starting writing more and more, and as time will go, hopefully Lavan will add more features so that it can be used in future as a good meta-analysis conducting package as well. But by now, we have a very good and very robust meta-analysis conducting structural equation modeling package within R, and that is called metaSEM, written by Mike Chung. And metaSEM is based on OpenMx. So OpenMx is a very useful and all-encompassing structural equation modeling package. However, in this workshop, I'm not going to cover that, because that's another large, big topic in itself. So we'll have to take some cuts. However, I am going to show you using metaSEM, what are the different codes that you can work with. And this is so intuitive, it's almost like a black box. So we'll have to probably unpack some of those things as well. The last thing that I wanted to draw your attention to is a software tool, which is referred to as ONIX. It's called actually Sigma Nix, but for English-speaking people, it could be called as an ONIX. It's a German website, but it is a nice Java program where you can draw structural equation models, and you can generate Lavan codes and OpenMx codes and all sorts of codes, and you can then run it if you have the software available. So I'm going to show you how it looks like, and here is a download page for structural equation modeling ONIX, and here is the home page for ONIX, and it's a very sparse, simple home page, and I'll show you how we can use ONIX to create structural equation models. So those were the three preliminary things that I wanted to talk to you before I went ahead. And off we go. So the first question that I have for you is coming up now in your Google Docs document. And it says that as a researcher or as a reader of research and meta-analysis and things like that, how many outcomes have you seen reported in research papers? Only one, two at most, at least two. So if you can put a cross mark next to the options, that would be really useful, and then we can launch into some discussions. So quite an overwhelming number of people are already started answering that at least two something that you get to see as outcomes in the research papers that you get to read and the researches that you do. Yeah. So it's almost never in our real lives that we have only one outcome for one intervention. Although when we start writing about PICO questions for conducting our search before we embark on meta-analysis, you will see that quite often it's one intervention and one outcomes. And that's kind of a framework that's very commonly used in almost in a number of different disciplines. Although you know that it is practically the way it works is this, that we get many outcomes for an individual exposure or an individual intervention. That is the norm. So it is also therefore possible that these outcomes are correlated with each other. So one outcome kind of feeds on the other. I'll give you an example. At the moment, we are conducting a study where we are looking at how organizational practices. So people in, practices that are used in several offices or workplaces, such as, morning yoga or meditation practices or policies, how do they impact psychosocial outcomes of the workers in those workplaces? In other words, how does workplace-based interventions impact psychosocial outcomes of the employees in those workplaces? And we are conducting a meta-analysis. There have been numerous studies. We identified something like 100+ studies, and then we are now binning them into separate groups. And we are seeing invariably that the psychosocial outcomes that we are reporting are something like anxiety, depression, people not reporting for work, people, high rates of attrition from the workplaces, and so on and so forth. Now, you can understand that some of these outcomes are closely related to each other. Say anxiety and depression are kind of related to each other. Now, if we conduct separate univariate meta-analysis, then we can get individual snapshots of what are the outcomes for individual interventions. That is informative. But it is far more informative if we were able to conduct meta-analysis where we were able to show how do these interventions work when we take two variables taken together. And that is the challenge of multivariate meta-analysis. Now, using standard meta-analysis practices as we do normally, we're using packages like Meta, but not so much of a metaphor. We'll talk about that later. It is useful if you use say, for example, Rifman, for example, for conducting meta-analysis. Very useful, very suited for using one outcome, one intervention. It'll give you all those things. Of course, there is the issue of network meta-analysis, but we are not going there yet. Now, when you do that, you are doing single variable meta-analysis, and that has been a standard practice for many, many years. So what does meta-analysis look like when you take two variables that are correlated with each other together? How would it look like? So that's a challenge that we need to understand and see whether we can do something to do it, do that kind of stuff. Another challenge.
I didn't get that. Could you try again?
Another challenge that we quite often face is that in many sciences and in many fields, we see that people report not individual estimates, but they report correlation matrices. It's a very common practice, say, for example, in twin studies, where you deal with or with environment and gene-environment interaction kind of studies, where you start with correlation matrices. So therefore, there is a case to understand what do those correlation matrices tell us. So rather than only looking at something like coefficient alpha or a point estimate, how could we use to synthesize entire correlation matrices and then reanalyze them together? So in other words, take these things and synthesize the correlation matrices, generate a synthesized correlation matrix from all the individual component studies, and then analyze it ourselves. That's also, your research and evidence synthesis and meta-analysis. Now, using standard meta-analysis tools that we commonly use, it is quite difficult to do that. It's impossible to do that because they're not set up to do that kind of work. Those are some of the areas where structural equation modeling shines. But before we get to the nitty-gritty of structural equation modeling and show you some of these things, I would like to take you back to my lecture where we would like to talk a little bit about and maybe discuss a little bit about what does it mean to do meta-analysis. Well, at its most basic level, if you think of a study, what we are trying to do in a study is we are trying to estimate a true population estimate of the phenomenon that we want to study. Say, for example, in our case, if we were going to study what is the association between organizational or institutional practices or workplace interventions and psychosocial outcomes, then perhaps we are studying it using a standardized mean difference or Hedges G, whatever it is. What is it in the population? If it were offered in a larger section of the office populations everywhere in the world, what would a particular intervention's outcome would look like? Let's call that mu. But what we have in hand is the observed effect size from an individual study that we then synthesize. So that's why we have given it a hat called theta hat. K is a case study in which you get to see this, but that is trying to assess the true population estimate. But then there are a couple of other things that we need to think when we start thinking in terms of meta-analysis. One of them is this, that an individual study always consists of individuals that are included in them. In other words, it can be human beings, it can be widgets, it can be other things. And these vary within the study themselves. So that's why we call it epsilon for a particular study K, and that is the variance of that study. So it's a within study variance. But then we go a step up, and what we try to do is this, that there are many studies that are put together, and these studies themselves vary between them. And that's the one that we are putting here in the form of a tau. So you see that for the Kate study, you can still see this. And you could say that, Arin, what you're showing us is essentially one of a random effects meta-analysis, estimation. And I say, yes, that's true, because what happens in a fixed and random effects meta-analysis is that, we'll come back to that later. We'll ask you that question later. But for the time being, let's look at it like this. So what the within studies, variance does is it gives you the variance of the studies. That is the studies locally within the studies themselves. And tau squared is the one that we get for between studies variance estimates. So if we put them together, then we get a complete picture of what the total variance looks like in the entire corpus of evidence that you want to synthesize. Here is a metric that we commonly use, and that is the comparison between, or the proportion of the total study variance, which consists of the tau square, which is the between study variance and within study variance, the V, and what proportion of that is constituted by the between study variance. And that gives us a measure of how scattered our studies are, the estimation of heterogeneity, and commonly expressed in the form of I squared. Now, in health sciences, in medicine, to some extent, we have got a rule of thumb. We say that if I square is something like 25% or lower, we say it's low heterogeneity or homogeneous, quote unquote, 50% moderate, 75%, 50 to 75% low to moderate, medium to moderate. Beyond 75%, the studies are very heterogeneous. So if they're heterogeneous, we tend to do some kind of a modeling. If they are not heterogeneous. If they're homogeneous, we do another kind of modeling, right? In meta-analysis. So here's my question to the group. What is your take on fixed and random effects models? Let's have some conversation on this. So this is not something that I have put up. Or you could put your answer in the Google Docs if you wanted to write something on the Google Docs, or if you wanted to open your mic and say something, more than welcome. So I'll stop for about 5 minutes and let's discuss this and see how we go. So what would you say about tests of heterogeneity and about the relationship between fixed and random effects models? So what are your take? What are your preferences? What do you do? I'll tell you some stories that we had I had experienced before, but I want to hear your impressions. Anyone? Any comment on your take on fixed effects versus random effects meta-analysis?
I'll make a comment if I can.
Yes, please. Go ahead. Yeah.
So in my field, in sort of conservation ecology, more conservation than ecology, with our heterogeneity is so huge that we're told never to use really fixed effects, because it doesn't really make sense to use a fixed effect with that amount of heterogeneity, I think.
Yeah. So again, I mean, it's a matter of field, of course. It's a very good point, Matt. And yeah, before I tell my story, I'd really like to get a few more impressions and comments. There's one comment that has come up in the Google Docs is that random takes care of the variability across data sets, but not using all the data, but considering that the studies are like a random sample of all the studies in the universe that they're there. Okay. So we will let this conversation run for about another 5 minutes to see how we are doing. Any other comment, anything that you have experienced from your field, like Matt was mentioning that in conservation ecology, and I'll tell the story of what I had experienced one time in another setting, doing meta-analysis in randomized control trials only.
Yeah, I'll make a comment. Yeah, I guess I'm just beginning, so I'm a complete newbie to this, but we're sort of using random effects models for accounting for repeated sampling designs. So yeah, and then so I guess it's hard to do that with a fixed effects model.
Yeah, good idea, Matt. Any other comment? Anything else? What other comments do you have? There's one comment that has come in Google Docs is they differ about the true effect assumption. Yep. Random effects model was used as if they can magically solve the heterogeneity. That's a very interesting comment. We'll take a look at it in a bit to see how these things are related. Many years ago, we were doing some work for the government, and what they preferred at that time, and they still do, I suppose, is when you synthesize information, when you do, they used to commission us to do what is called systematic reviews, which means that we would look up by using a standard set of questions, a number of studies, and then we would be summarizing the results of the studies. And if that was warranted, then we would be conducting what is called meta-analysis. And one of these policymakers once told us that if you face there is heterogeneity, then do not synthesize anything. We are only going to use studies that are homogeneous. So give us only fixed effects, meta-analysis results, and things like that. And, and we were wondering, oh, well, hold on a second. What is going on here? And so these things have become such a bone of contention that quite often you will find that many people will cull studies. So you get a large number of studies, and then you restrict your selection criteria to such an effect that you get a very, very small sample of studies, and you just derive your point estimates only based on those studies. Now, you may wonder that such an approach is quite limiting, because in effect, what happens is that fixed effects meta-analysis is a special case for random effects meta-analysis. So let's go back to that equation a little bit and see what is going on here. Now, this graphic comes from Matthias Herr's excellent program, Demeter, and his accompanying book. And I encourage you guys to take a look at the book. The book is really good because here is the book called Doing Meta-Analysis in R, hands-on guide. It's very nice. And this is taken from the chapter on multi-level meta-analysis that he has put up in that book. So let me explain what I mean by this in here. Now, when you start thinking in terms of meta-analysis, you start thinking in terms of where do these data came from? Well, citing examples from health sciences and medicine, for example, I say that these data came from human beings, or these data could come from an environmental sets of objects. The data could come from widgets. I mean, it does not, without going into the nitty-gritty of who our units of analysis were in the first place, let's say these triangles represent human beings. So these, in a sense, the participants, the units, are our level 1 from where our within study informations are coming from. So now you see that that distribution pertains to this particular study, and a variation is arising from there. And what happens is that researchers, when they report their studies, they synthesize that information at the participant level, and then they give you a point estimate and a variance around that point estimate. Then what we do in meta-analysis or evidence synthesis is we take those point estimates and the variance that arose from those individuals in those studies, and then we synthesize them at level 2. And when we do that, we are now getting it a notch, a level up. That's where we get our analysis from. So the levels of variation that we get here are the levels that, if these studies were the only ones and nothing else, then we might as well have stopped at that level and just synthesize one report and be done with it. But because there is so much variation that we normally expect, therefore, a random effects meta-analysis is probably a more natural and normal way to do everything. And then we decide whether we are going to set the tau to 0 so that we ignore the random effects constraints. And we say that we set the random effect constraint to 0, we report only fixed effects. If the fixed effects and random effects closely match, and if we have got reasons to believe that there is not much heterogeneity, the studies are homogeneous, if they pass the test of homogeneity, then we report fixed effects, and we show that fixed effects and random effect meta-analysis are the same. But essentially what we are doing is we are conducting a two-step model in conducting and in generating our point estimates in the form of a meta-analysis. But wait, there's more. Because if anyone who has ever read a meta-analysis or has conducted a meta-analysis knows that we do not just leave at the point of reporting a point estimate, but what we instead do is that we start binning the studies. Okay, so we cluster the studies in various different clusters, perhaps the studies that are of good quality, studies that are of poor quality. Perhaps we cluster the studies based on certain countries. We can cluster the studies based on some other parameters that we think that are quite important. There is another thing that's also very important in case of meta-analysis, and this is the case of meta-regression. And this is a particularly important piece of work that economists often do when they do meta-analysis, because they take often, hundreds of studies taken together. And for them, meta-analysis has got a meaning where they take variables that are contained within the studies, the point estimates, partial correlation coefficients, and what they then do is that they run regression models on those studies, on those point estimates, and that's their meta-regression. That's also very important for us. Meta-regression in the context of medicine and public health is often also referred to as sensitivity analysis, where various parameters are tested to see whether they have got a bearing on the effect estimate. But so what we are trying to do here is this, that we are binning the studies, we are categorizing the studies, we are clustering the studies, and then we are examining them. And that is important because this information came from somewhere. So in effect, your random effects meta-analysis tau square is a composite of two of these things. The whole of it is your random effects meta-analysis, but then you can divide it into two parts, one in which what are the effects of the various other variables that are in my meta-analysis that has got a bearing on the results. So our meta-regression becomes incorporated into a meta-analysis by itself, by default. This introduces a third layer. And so that third layer is, so now you know that meta-analysis essentially is a three-layer multi-level problem, of which the random effects meta-analysis is a special case, which is like a two-level meta-analysis. And on one level or single level meta-analysis, the fixed effects meta-analysis is a special case of the random effects meta-analysis. I'll stop here because there's a lot of things that I've bombarded you with, and I'll take some questions and some thoughts and observations. Over to you guys. So what do you think? Does this make sense? Does it make no sense? Am I fuzzy? Am I wrong? Right, the floor is open. Let's say for the next 5 minutes, let's have a discussion on this. What do you think? What do you guys think? Perhaps I can break the ice and say, who among you do three-level meta-analysis? All the time? Neil?
I think I've done some of these before where we've had, study level heterogeneity and then within study level heterogeneity, if I'm understanding it correctly.
Mm-hmm. Yeah.
Feels comfortable.
Yeah.
I think this hierarchical idea strikes a chord, because when you're extracting data, you'll find some authors provide really detailed data, and maybe you can do like you have an individual level data,
yeah.
And you have to, so this kind of way of thinking about it makes a lot of sense.
No, thank you, Neil. Thank you, Matt. Some other thoughts. Anders. Anders, you're muted, are you?
Maybe now?
Oh, now you know. Now we can hear you. Go ahead. Yeah.
That's saying yes. Can you hear me now?
Yep.
No.
Yeah.
Okay. Any other thought? What are the thoughts that you had? Okay. So the idea here is this, that anytime you are conducting a meta-analysis, whether you acknowledge it or not, and anytime you're using what is called a meta-regression within a meta-analysis to identify what are the effects of various other variables that were noted in the studies, anytime you are abstracting information from a study where you are incorporating and including other informations about the study that may have a bearing on the outcome, you are conducting a 3-level meta-analysis. You're definitely conducting a 2-level meta-analysis. The only thing is this, that you're setting your parameters such that you're confining yourself into a fixed effects meta-analysis and doing a level 1 meta-analysis. But basically, you are doing you're doing a 3-level meta-analysis all the time. And we will see that in a bit, that it is the nature of the game when you're doing an univariate meta-analysis most of the times. Anders.
Okay, I'll try again. I think you heard me at the end last time. Yeah. So I've never done a meta-analysis before. So just coming from as a naive first-timer, how is this any different from having a field ecological study where you have samples in different forests or countries? You would never not do a hierarchical mixed effect model because the tools are there, they're easy to use. You would never just do a fixed model just by default. And if you found that there was no sort of between no variation between the random effects, then you could drop them. But why would you? Well, what do you have to gain? So why is it different in meta-analysis?
Oh, it's not different. It's just what we tend to do. It's kind of you know, we speak in prose, that kind of a thing, you see. So there's not, I mean, when you will start realizing that, okay, yeah, we are doing this all the time, you see. Yeah, we just don't say it like that. We are not saying that we are doing a hierarchical linear modeling, but we are actually indulging in that kind of an exercise, and we are doing this work. So let me recap once more what we're doing here.
Yep.
When we are doing evidence synthesis, we are dealing with papers, right? These papers contain results from individuals. And these individuals could be individual human beings, could be other entities, whatever that is, individuals. Yeah. So the results contained in the papers that we report as point estimates and variances are the ones that came from some people somewhere. These people were different, right? And that's the reason why we have got a point estimate and variance around reported in the paper. Then, and that's level 1. If you wanted to just do that and do nothing else, fair enough. Okay, so we would have to assume at that point is that these papers were just in themselves enough for us to give everything that we wanted to do. We would summarize them and we're done with it. But in real life, that's not the case, as Matt was mentioning earlier. Yeah, in your, say in ecology, for instance, and definitely in case of health sciences and many others, where we can never assume that that's it, because there's so much variety, there's so much heterogeneity. Then we say a step up and we say that, look, you know, we now need to account for what happens if these few papers belong to a universe of similar papers, which means that they are a random sample of all the papers that we could get them. So that's where the level 2 comes into the picture. But then we go a step up, because even though those papers were there with us, they were clustered. Yeah, not everything is coming from 1 unit, exactly as you were saying, Anders, that, okay, I'm going to get something from, maybe from forests. Another one is going to come from, say, studies that are focusing on wetlands, and some are coming from, say, some other geographical regions or some other environmental situations. And now I'm going to synthesize, but I can't synthesize everything like apples and oranges. So that's where the level 3 comes into the picture, you see? Yeah. And in our analysis, that level 3 gets noted in the form of a meta regression set. So we get this, all of the other variables, and see how would our effect estimates would vary if we wanted to take into account those clusters. And there are ways in which we can do this. So if this is a multi-level exercise at all times, then what are some of the tools and what are some of the approaches that we have in our toolkit? A very useful toolkit is to use a package called Metaphor, which is very useful. But what I'm going to show you in this workshop, and we can workshop on this, is the use of structural equation modeling. So let's deal with structural equation modeling a little bit. Now, here is what this world looks like in a structural equation modeling world. And let me explain this. Let me minimize this now and see what questions do you have. A part of your screen is black, not sure why.
Yeah, it's just that window that's, there's another window that you just moved. That's it.
Okay. Now, can you guys see my my screen well? Is my screen visible to you all?
Yeah, it's good.
Okay. So this is what it looks like in the world of structural equation models. So let me explain this. Before I went ahead and made a fool of myself, I just wanted to make sure. How many of you are already familiar with structural equation modeling? Just a show of thumbs or hands up or whatever is going to be useful. So Matt Jones, Zainab, Matt, both Matts, Erkan. Okay, and there are a few of you who have not used SEM before. There's a thumbs down from Arthur. Is that because that you are, all right, there's a thumbs down from Bettina as well. What do those mean? That is that you're familiar with it or you don't like it or what? Whatever, I take it that some of you are familiar, some of you are not. So those of you who are familiar, of course, it needs no introduction, but those of you who are not familiar with the symbols and languages of, the other window has come up again. Okay, I'm going to do that again. That's because of this. How about that? Can you see me now? See my window now clearly? You say yes, something?
Yep.
That's great.
Okay, yeah, all right. So those of you who are familiar with structural equation modeling, it will need no introductions and maybe a bit slow, but those of you who are not familiar with structural equation modeling, what you are seeing here is the presentation of a two-level meta-analysis, how it would look like in structural equation modeling. So from left to right and from top to down, you see that there is a triangle, and that triangle is called a constant, and it always receives a value of 1. Then you see that an arrow extends from the triangle to a circle, and that arrow will have different meaning based on different contexts. So in this particular context, the arrow means that beta underscore r is a mean random effects. Okay, I have just given it a value of 1 arbitrarily. So don't look at that number 1.0. It's a pre-assigned value, but beta underscore r will assume or we get some value, and that's the mean of this mean of the effect size that you do get to see there. Okay, so that mean structure here, the constant is lending that mean value to F1, which is a circle. And that F1 that you get to see is what is known as an unobserved or latent variable. This variable is not something that we get to see. We do get to see the square box, which is our point estimate of an individual study, but we do not get to see from where do those observed variables arise. So basically, this is why that circle, which is an unobserved or latent or hidden variable, then explains the variation in the manifest variable. The curved arrow that you get to see with two heads is either a variance or a covariance. If it occurs in between two variables, then it's a covariance. If it occurs only in the context of a single variable, it's a variance. So that is my tau square, which is the variance of the random variable that is present here, which is a representative of the between studies. Okay, so we call that a random effects latent variable that will assume a particular that will assume a value of its random effects, which is based on a mean structure that you get to see here, and its variance is a tau square that we will be estimating in the model. But in the within level studies, that is in the individual study level, we know that there is a point estimate and there is a variance. So that's the V_I is the unexplained variance that we get to see for X1. And all other variability is explained by that random effects effect structure here. Okay. So this is going to become a little bit clearer as we start diving into structural equation modeling a little bit more, so that it'll start making sense. But for the time being, I will request you to hold on to your mind that there are two levels of this analysis, because I just wanted to simplify things for now. I did not include a third level here, but a single level, a two-level meta-analysis looks like this. There is a within level, there is a between level, and with the between and the within level, we are getting a full picture of a random effects meta-analysis. So why is this important? Is because if we can set the tau square to be 0, then this arrow moves directly from here to here, and we don't need to worry about that because that's going to be our fixed effects model. So we can manipulate this. We can manipulate this variable. We can set this variable to 0. And when we do this, it's going to give us our fixed effects meta-analysis. Okay, so we can easily switch between random effects and fixed effects meta-analysis in the conceptual understanding of conducting a structural equation model in order to conduct a meta-analysis. So before I went ahead and showed you with codes, I just wanted to dive in a little bit in some structural equation modeling chops. So that's why I am going to do some worked out examples. We will be using metaSEM. Before I dived into that, just because a few of you have not used SEM before, maybe I can show you some of the structural equation modeling stuff. Okay. And so I will be moving in between an Rstudio instance, and I will be moving in between an Rstudio instance and some visualizations, and this screen. So I beg your pardon if you have got your Rstudio instances that you wanted to play along. More than happy to do that. So Matt's question was that, so is the one constant like the tilde1 bit in your random effects model? Exactly. That is exactly the point here. Yeah. So one constant is like that one. Yeah. It's set. Well, it's a little bit like it's not that one then vertical bar, but that's the clustering variable. What we are doing here is not really clustering, but giving a intercept or a mean structure. So think of that triangle, that one constant, lending as an intercept in a regression model, rather than the vertical bar. So we are not yet using the clustering or indicating the levels. That's a different concept. Does it make sense, Matt?
Yeah, I think so. So can I have a look at this slide again? Sorry, the
Sure.
previous one.
Yeah.
So your response variables below the dotted line, that's your effect sizes.
Yes.
Yeah. Okay. And then you've got
So think of this one as a regression model. So X1 is regressed on F1, yeah?
Yeah.
And F1 receives a mean from here because F1 explains X1. X1 has got its own variance that is explained by F1, which is an unobserved variable, yeah? That will explain the variation in the X1. Yeah. And in setting up that regression equation, we will have an intercept term which will come here, but the mean of that is given by beta r. Okay. If we had an arrow that went from here to here, that would be the intercept term, but that's not relevant here. What's relevant here is the random, random mean or random effects.
So there's no fixed effects here yet?
No.
Okay.
The fixed effects is only going to come if we set this to be the tau squared to be 0, because then the random effects doesn't make any sense. There's only one, and that's the fixed effects that you get to see.
Okay, thanks.
Yeah. Once we get into that exercise, you'll see what I mean by this. Or we can come back to it again. All right. So let me bring up the RStudio Cloud and I'll show you a few other things that are quite interesting. So I will resume from my sleeping RStudio and see how it works. So quick question to the group. Can you see my RStudio once it boots up? And if you can kindly give me a thumbs up, then I'll know that you can.
We can see it starting to load. So.
Oh, okay. So let me see if I can. Right. Can you see an RStudio kind of set of?
Yes, we can see it now.
Codes and codes and codes and codes and codes and codes and codes. Yeah.
Yeah.
Yeah. So that's something called argchunk1 and all that kind of stuff. Cool. So, all right, let me go back and see what I can do in this hour. Now, this is again for those of you who are new to structural equation modeling. You will see several of these symbols. Okay, so the square symbol means manifest or observed variable. The circle means latent or unobserved variable, which means that a variable that you have not seen or you don't know, but you're going to measure from the measurement variables. The arrows means directional relationship, which means that, okay, if there is an arrow that goes from a circle to a square, then that circle, from that circle to square tells you that there's something going on there. That latent variable is either explaining the manifest variable. If there is an arrow that goes from this constant to a square or a circle, then that is either a mean or an intercept, depending on what kind of variable we are working with. If it is an exogenous variable, which means that if it's the variable that is going to explain something, then that is a mean. But if it is an endogenous variable, which means that if it is a variable that has been explained by something else, then that is going to be treated as an intercept in a regression equation. So that directional relationship depends on the context in which it is present. And then there is a non-directional relationship, which means that this is either a covariance or a correlation or even a variance. When one variable varies with itself, then that's a variance. If one variable varies with another, then it's a covariance. I was too fast. So what questions do you have? Let's see if there is a question in the chat box. So could you perhaps say something about the utility of piecewise SEM in all of this? Advantages maybe to mix and match error, yes, and familiar coding, yes. Yes, piecewise SEM is exactly what you will be doing when you will be doing this kind of work, although you need not always do that. But piecewise SEM is essentially what we are doing here. Okay. So let's start with a very simple simple instantiation of a very simple. We call that as a measurement model. Okay. So OpenMx is a program where you can do this. You can create these diagrams in OpenMx. It's really very simple to do this work. And I will leave this exercise with you rather than showing it here, because it's a little bit time consuming to draw all the diagrams and arrows, but perhaps I can show you as well. So I'm going to stop sharing the screen here for now. And then I'm going to show it there, right? So I'm going to stop share for a minute, bring up the OpenMx screen, and then I'm going to share the screen again. So now you guys should be able to see an OpenMx screen. Can you? If you can see a screen that says OpenMx, yeah, thank you, Matt. So this is an OpenMx framing or OpenMx formulation of a structural equation model for what is called a measurement model or confirmatory factor analysis model. So what happens here is that this circle called G is a latent variable. This variable remains unobserved and will be measured using the manifest variables info, simul, word, matrix, and pict. So just to give you a background, it's from the Wisconsin questionnaire where people were asked on a number of questions in terms of understanding their common intelligence measure, which is called a G. And these were entered into a correlation matrix. And what happens with these arrows is that this G is trying to explain, this G explains the variation in the manifest variable info. And this bit A here, of course, is 1.0, but that's a starting value, but A is the path coefficient that goes from G to info. And that path coefficient, if you square it, then you give its explained variance, which means that what proportion of information's total variation is explained by the common intelligence or G. But that would still leave an unexplained variance, which is the error variance, and that also is unobserved. And we assign it an, therefore we assign it a latent variable status. This is error variance. We fix it to some values, perhaps a path coefficient that goes from the error variance to the information variance. And that tells me to the extent to which this one is explaining the variation in the information as a variable. So what you can do in OpenMx is you can create variables. So I can right click on this, and then I can create a variable. Maybe I want to create an observed variable. It will create an observed variable. And then I can select on the observed variable, or I can select on the latent variable because I want an arrow and add a path from the latent variable to go into my observed variable. Right click on this, add a path, add it to my observed variable, and the path gets added. And then I can tweak these path characteristics to suit my model to work with it. Likewise, I can add another latent variable, which is going to be an error variable, which is another latent variable. And when I do this, I will draw an arrow from this latent variable to my manifest variable, and it goes there. And then what happens is this, that if you have got a data available here, you can generate a script that will give you, hold on. You can generate a script. Of course, it's not working, behaving well, but you can generate a script that can either be in OpenMx, that you can use in OpenMx as path model or a matrix model, or in many cases, you can use a Lavaan script, which you can then directly input into Lavaan program, and it is going to run. So you see that structural equation modeling, once you get to know the theory of it, has become pretty easy and trivial nowadays to execute in your real life using a tool like OpenMx and Lavaan. But let's set that aside and let's come back to our screen where we started. Okay, how about that? So I'm going to stop sharing the screen and come back to the screen that I was sharing before. So using OpenMx, we had drawn a diagram like this. Let's see, there is a chat question. Oh, Matt says, oh, that's nice. Good. Thank you, Matt. So we have created this confirmatory factor analysis with OpenMx. And now what we're going to do is we are going to generate a script by hand in Lavaan, or we could do that in OpenMx as well. And then we will specify a model, then we'll fit the model, and then we'll examine the model in that order. So we start with data, then we specify the model, then we fit the model, and then we are going to examine the model, and then we can modify the specific parameters of the model and then re-specify the model and work with it. And the cycle continues till we find a good model, the best model that we can work with. And remember that all models are wrong. Some models are useful. I mean, you know, as George Box used to say. So this is the code. Okay, let me go over the code slowly so that if any of you are willing to write it in Rstudio, maybe I will show you how it looks like in Rstudio and then we can run it. But meanwhile, let me explain this. So in Lavaan, I'm going to create a matrix. Now it's a lower triangular matrix, as you can see. It's a correlation. So you can see that 1, 1, 1, 1, 1 are the variances, and the lower triangular matrix of 0.72, 0.64, 0.63, so on and so forth. These are the correlations between these various variables. The column names and the row names are same, and these are for similarity, word for word reasoning, matrix for matrix reasoning, picture for picture completions. These were the items that were used in order to infer the general intelligence. Because this is a correlation matrix, I want to work with a covariance matrix because that's what the structural equation modeling prefers to use. And if we use this, we have to provide them with standard deviations. These are the lists of standard deviations of these variables. Again, we need to provide the names of these, same thing as these ones. And then I can convert the correlation matrix, which is this, into a covariance matrix using cor to cov function. All right. In the next stage, what I'm going to do is I am now going to specify the sample size. In this case, it's 500. And here is where I'm going to specify the model. The model is that G, as you can see, the G is here, and A, B, C, D, E are the path coefficients. So A as a path coefficient for the variable info, which is the observed variable. B is the path coefficient for the observed variable simil, and so on and so forth. I have created this model. It's a single line, simple model to work with. Then I fit the model with CFA. CFA stands for confirmatory factor analysis. It's a function that takes the model and that takes the covariance matrix, because that's the data that it wants. And I have to provide at least the sample number of observations. Once I do that, I can ask for a summary of the fitted model, and I can ask for a standardized estimates of everything that I got. So when I do that, I get a standardized estimates. And I would say, for example, in case of information only, I have got that the explained path coefficient is 0.857, and the information's standardized information is 0.265. It turns out that if you take its square, like if you make its variance, and if you make its variance here, you will be able to add them up, and they will add up to 1, because that is going to be the total. This is unexplained variance, and this is explained variance. This is the part of the variance of the info variable explained by G, and this is the part that is unexplained, that remains as its error variance. Okay, so this is the communality factor, and this is the unique variance that we get to see. Okay. Again, I'm sorry, I apologize, I was too fast, but this is in general how a confirmatory factor analysis runs. We now come to another thing that's called a mean structure, and that's where I'm going to explain things a little bit. And I'm going to show you, if I can show you with a mean structure, and then I'm going to go and show you how it looks like when it comes to meta-analysis standard equation modeling. Now, in a mean structure, we have got something different. Now, remember that this is a constant, and the constant always gets the value of 1. This is my latent variable, and these are the variables on which I made some measurements. What I'm trying to do here is that using the latent variable, I am explaining the variation in each of these 5 manifest variables. Okay, so A is the path coefficient, so A square is going to be part of what I'm going to explain in terms of the part of the variation in x1 that will be explained by LV. And the way that works is this, that x1 is regressed on xv. In the language of path analysis, we call LV as an exogenous variable, because LV does not need anything else to explain itself. It is the one from which we are starting. X1 through X5 are called endogenous variable because they are within the model that are explained by LV. Now, when we try to find out the mean structures of these, you see that alpha becomes the mean of LV because one is a constant, and from the constant we get, when the constant sends an arrow to the LV, then it becomes the mean of the exogenous variable. Whereas because these are your endogenous variables, because these are the variables that are being explained by LV, mu1, mu2, mu3, mu4, mu5, I think I mixed it up. Sorry about it. So this is my intercept term, and these are the means that I'm explaining here. Okay. So when it goes to an endogenous variable, they become their means. when it becomes their exogenous variable, when they are trying to explain something, then it becomes its intercept term. Okay. So alpha is the intercept term that we are going to use for the LV, and all of these things are the means that are unobserved, but they are estimated means of these various variables. Okay. So if we now put this understanding into the model of a meta-analysis, this is what we get. Okay. So in our understanding, x1 is the observed variable that we get for each study, and f1, which is the random effects model, is the one in which that is trying to explain the x1. So that's the random effects. Yeah. And the random effects is trying to explain this. So this is the intercept term, but that's the that's also the our random kind of random effects. So that's why I call it beta R or random effects value that we ascribe to it. And so we can explain, we can put this in the language of metaSEM or meta-analysis using structural equation modeling, using a library called metaSEM. So metaSEM is the package which will make doing these things a little easy for us. There is a data set built in metaSEM called MAK09. And we'll just take the data set, and it's a data set on, I think, the risk of atrial fibrillation, which is a heart disease, amongst people who take two kinds of medicines, biphosphonate or non-biphosphonate. So they're kind of a drug. People are taking the drug, people not taking the drug, and they were conducting a meta-analysis on that. So, that's what you're going to get. And then what happens is this, that for each one of them, I have selected the point estimate and the variance around the point estimate, and then I ran the meta. And what is important here is this, that if you are using both meta as the package within R to do your regular meta-analysis and meta-SEM, then there is a name conflict. So you will need to unload meta from your workspace and keep only meta-SEM to work with. Otherwise, this is not going to work. This is a problem with meta-SEM, so that's something that you need to keep in mind. But if you use something like meta4, there's no problem at all. And then you get the summary. So let me run this in Rstudio and show you. There's a question in the chat. So 1 times alpha is LV, yes. Correct. So let me show it again to see how it looks like. See whether that makes sense to you. All right. So here's what I have done. I have loaded the library called meta-SEM, and then I have loaded the data called MAK09, and then I will have asked for looking at the header of it, and then I've given you the types of treatments, and then I have selected the YI/VI, and then I've run the meta. Okay, so let me run everything one by one. So once I load the data, once I load the library tidysim and these 3 things, it'll load the data. And if I ask for the head of it, this is what it looks like. So for the first 6 studies, it's either an RCT or an observational study. We're not supposed to mix up these studies together, but let's say we have done this. And then what you do get to see is this, that this is the YI, which is the point estimate. And this is the VI, which is the variance around the point estimate. And I think what they're trying to do here is the relationship between the treatment and the atrial fibrillation. What were the correlations? Now, if you go to make this analysis, this is the object MAC as a random effects model, and I'm going to run a random effects model using the meta-SEM. If I do this, then you will see the results of a random effects model coming up here. Okay, so intercept is the one that we were talking about earlier. Intercept is a random effects model. So when we talk about that, that's the intercept that we talked about, the beta R. And that in this case has turned out to be 1.80. And the tau square, which is the combined random effects variance, is actually very, very small. Okay. All right. Question to the class. What do you think is happening here? What kind of a, without looking anything else, what kind of a meta-analysis would fit here? What would you do? Again, we fit a random effects meta-analysis, but we might have as well fit a fixed effects meta-analysis. It will make no difference, right? Because look at it. The I square is 0. Yeah. This is a toy study. We only got 8 studies here. Okay. But this is what you do get to see in this case. Let's say if I wanted to fit a fixed effects model, how would it look like? In that case, I would make the RE constraints, that is random effect constraints, to be 0, which means that in this case, I would force tau square to be 0. Okay, that would turn this random effects model into a fixed effects model. Okay, and if we do that, see what happens. It will still give you an intercept, and this intercept is the same thing, because what happens is now this one moves this arrow to here because this doesn't exist anymore. Yeah, so this is still an intercept. Yeah, because there is an imaginary variable here which has got a tau square of 0, so it becomes a phantom variable. Okay, a phantom variable is a variable which is like a latent variable with a 0 variance. So then we get an arrow that comes from here to here, and this is the intercept term. Now this becomes its own intercept, and that intercept, so therefore this times this becomes the BF, and beta F now is no different. It becomes basically 0.180. Remember that the one thing that we had seen before was 0.180. Yeah, 1.80 times E. Yeah, so 0.180. Same thing here is 0.180. And again, you can see that I square is 0. So a fixed effects model is probably a better fit, or you could do with a fixed effects model. You don't really need a random effects model, although you can report a random effects model. No difference between the two. So that's an example where you see an univariate meta-analysis where you can switch between fixed effects and random effects model using a structural equation model, but it's a conceptual understanding that's quite important. And you might wonder, hey, what's the big deal? Why do you spend so much time talking to us about something that you do anyway in other things? Here's the magic. What happens if you've got 2 or more outcome variables with the same intervention, and if these outcomes are correlated? If they're uncorrelated, you can use univariate meta-analysis, doesn't matter, no one bothers. But here is where your traditional ones are not going to work as well. So here's what we are going to do, okay? Remember, the same model works. It's the same thing, except now, instead of one F1, I have added another one, and have added another manifest variable. So now it looks like this. But what is more important is that these variables are correlated. So this is a covariance term that I can add. And therefore, there is a covariance between their parent unobserved latent variables. Okay, exactly as before, they are going to give us the intercepts. So we're going to get 2 intercepts, yeah, and 2 tau squares, yeah, and a covariance term, because that's very important for us. So let me give you the code for the multivariate meta-analysis. In this case, we are going to use a data called BCG. And here he was talking about people who are vaccinated, their odds, versus people who were non-vaccinated, their odds of getting tuberculosis. So they have given us 2 Ys. So and odds in the form of people who were vaccinated, people who were not vaccinated, they were the point estimates. And therefore the variance of that natural logarithm, natural log odds of people who were vaccinated, natural log odds of people who were not vaccinated, and the covariance between the 2. Okay, because we needed these 3 things. Because we needed these 3 things. You want to estimate this, you want to estimate this, and you want to estimate this as well, because that's the order of your importance. And then what you do is, once you do that, you ask only for random effects. And similarly, you could use things like you could convert that into a log effect as well, but we are only going to go for random effects. And we may ask for equal intercepts, which means that we could say that, look here, what happens if we force the intercepts to be 0? And then what happens? Okay, so let's take a look at this first. Okay, so again, we have read the data, and then we are going to see what the data looks like. So here are first 6 studies. They were conducted in different years. And these were the ones in which you will see that, they were the geographical regions, random allocations or not. There were a few other variables. And these are the ones that they were talking about, okay? So they were talking about the odds of people being vaccinated, odds of the people not being vaccinated, the variance of the people who were vaccinated, their odds, the covariance, and those who were not unvaccinated. Okay, on this basis, they were deriving their point estimates. Now, this is a toy data. I mean, you could play with your real world data in many other ways, but I just wanted to show it just to make sense. So there is one point estimate, its variance, another point estimate, its variance, and the relationship between the 2. Okay, some of them may not be related, some others might still be related. So let's take a look at this one and see what we get out of it. If you do that, you do get to see that there are 2 intercepts and there are 3 taus. Because the intercepts there are 2 variables, therefore there are 2 intercepts, but there are 3 taus because these taus are variances and covariances. The first tau is a variance for intercept 1. Intercept 1 was for the vaccinated people. Intercept 2 is for the unvaccinated people. So tau square for the second group is going to be for the unvaccinated people. And the tau square, which is the one of our interest, is going to be the one that is going to be for the correlation between the 2, or in this case, the covariance between the 2, between the vaccinated and the unvaccinated. And we could ask for standardized estimates, but we didn't ask for it, but we could do that. And the other thing, of course, is this, that we could constrain the intercepts to be same, okay? And so we did that. we would get a single intercept for both, but we forced it. We said that, look, but I mean, this is a toy example again. I mean, if you wanted, you could get these two intercepts to be the same, because if there was reason for you to believe that these were kind of similar, made sense. And you know that these studies are quite heterogeneous, so random effects model probably makes sense in this particular situation. Where it adds values to us is it allows us to examine the individual summary estimates and the joint summary estimate. So take a look at this, and I'm going to explain that in a bit. If you plot it, you do get to see that you have got two effect sizes. So this one is for the odds of getting tuberculosis for people who are vaccinated, odds of getting tuberculosis for people who were unvaccinated. And what you do get to see here is a joint probability of that. Okay. And in each case, of course, they are going to give you a point estimate and a diamond, because these are random effects models. And then what you do is this, that around this, you get the confidence interval of the joint probability estimate of what is the likelihood that these people are going to get the, or what is the effect sizes or the joint effect sizes of these two things happening, two events happening simultaneously. And each of these are individual effects of the individual studies. And the large one is the is going to give you a large broad-based interval of all the studies that are taken together. Now, the advantage of this, of course, is this over univariate meta-analysis is clearly apparent, because now you know what is the correlation between these two effects, positive or the negative, or in which direction are they moving. So here, for example, you do get to see that the effect size of one is like around, yeah, you can see the two effect sizes of these two, the joint effect sizes of these two in the center diamond that you do get to see that are being reported. Okay, again, I've been too fast. Let me stop and take questions from you. So what questions do you have? What questions can I answer?
So we got two outcomes here.
Two outcomes.
Yeah.
Two outcomes that are correlated with each other. And those correlations are given in the form of a tau that you specify as a correlation in the input matrix.
Okay. And in the code, where's the bit where you specify the actual model structure? I couldn't see that in there.
Okay. So what has happened? This is the one that I talked to you about, but
yeah,
the black box nature of meta. So what happens in meta is if you bind, if you bind the two yi's, that is the 2 point estimates, and then you bind the variance, covariance, the variance, yeah, this, and then you indicate that I want a random effects model, it will assess, it will estimate using a statistical regression model. So that's the black box bit of it. But if you want, I can share you with the detailed algorithm that it goes through to do that. Unfortunately, this is the bit that we can't do in Lavaan. You can do that in M+, but not in Lavaan. Because what they do here is this, that they do what is called a random slope model to assess the level 2 for the random effects model. But you can't do a random slope analysis in Lavaan yet. That'll probably come sometime. So before we went further ahead, let's have a quick set of questions and answers. I mean, I admit that it was a very whirlwind and very quick introduction to a lot of very complex concepts. It probably takes several hours to unpack all of these things. So for that, I definitely would like to apologize that I went too fast with these things. And there are many, many things that I could not cover here, which I will list and talk to you what we can do going forward if you're interested. What other questions do you have? Are there any questions in the chat box, you know? Okay, one other question that came here is that does random effects model here in reality mean mixed effects? No, a mixed effects model is the one that we were talking about when you add in other variables in addition to the random variables, where you're predicting with these other variables the variation in the random effect size. So that's a mixed effects model. A random effects model is not the same thing as a mixed effects model. So I think that was a question that came up in the Google Docs. Was there any question in the chat box? Oh, can you think of something? I couldn't see anything in the chat box either. Okay, so again, I mean, it's kind of a whirlwind tour of meta-analysis, and I barely touch structural equation modeling here. And basically, the idea is this: that a structural equation modeling can be used to simplify meta-analysis concepts to some extent. So it kind of unifies the concepts of random effects meta-analysis. It layers. It tells you the levels of meta-analysis as 3, 2, 1. And using a structural equation modeling will enable you to do meta-analysis in ways that conventional packages will not always let you do that kind of stuff. Although if you use metaphor, you will be able to do the multi-level modeling pretty similar. But it gives you a more graphical way of looking at this world. There is another one that we have not covered here. It's called meta-analytic structural equation modeling. What that does is, of course, take the correlation matrices, put them together, and then reanalyze them. And we also have not shown you the 3-level meta-analysis, which means that, you know, what are the other variables that you could bring in and then build your meta-analysis. But you can probably understand at that point, all you can do is you add additional variables to this random latent variable, and then you know, fit the model to see how they would stack up with these ones. So there are quite a few things to explore. So what I have done basically is this, that I've set up a GitHub repo for this workshop, where I will be populating with more codes and more stuff. So if you're interested, please, you know, fork it, or, you know, if you like it, you can fork this and work with this. You can fork this repo and use it. So you can fork this repo, you can start this, whatever you want to do with it. And if you wanted to add some stuff to it, it's good. You can add pull requests, and we can build quite a community around that to get some more work done. I think I would leave myself there and leave room for questions and your final observations and comments and everything else. There's something on chat as well. What was that? Oh,
Just me putting the link to the repo there for you. Thank you so much, Aaron. That was brilliant. A lot to think about. I can already see where I can use this in my work. We have lots of things with correlated outcomes. Be quite useful. Are there any questions from the floor or from anywhere else?
Yeah, I'll start, I guess. I was just wondering. So one of the things you sometimes do with structural equation modeling is combine measured variables into one latent variable.
yeah.
I guess you can do that here.
Yeah, you certainly can do that here, definitely, because, well, you are doing it in a way, because what you're doing here is this, that you are, particularly with multivariate meta-analysis, where you are separating out two latent variables, yeah, and you're regressing them on the manifest variables, yeah. And so if you wanted to have more of these things, then they would have to be entered somewhere here. So which means that hierarchical latent variables come into, and then you can use them. So
Yeah,
instead of,
sorry.
yeah.
I guess
Yeah, you can make it as complex as you want.
Sorry.
Sorry.
Like, could this be used for something like where you have an outcome which is measured in lots of different ways?
Mm-hmm.
Yeah, I guess that.
Yes, exactly. So
Okay.
instead of this manifest variable, which is a very simplistic manifest variable here, you could have another latent variable with its own manifest variables that is going to make the measurements. Yeah,
Okay.
Of course you could.
Yeah.
Cool. Yeah, there's no end to that. I mean, the real critical part here is this random effects variables that you set up. What happens here is up to you.
Yeah.
Right. Thank you for that thought. Excellent. Yeah.
And does it deal well with like missing data? I vaguely remember that being a bit of an issue.
Yes,
sometimes.
that's the other thing that I did not talk to you about, the missing completely at random versus missing at random. And so what happens if you do two separate univariate analysis, you're using things like missing completely at random. Yeah. And so you are losing your data sets. Whereas here with multivariate data analysis, you can take a good look at both of these things together, because you could miss things at random. So Anders.
Yep. Hi. So it's a new question. So if you're not finished with the answer, you can do that. But
No, go ahead.
Yeah. I asked the question earlier about piecewise SEM. I was referring to this specific R package on CRAN. I ended up using this one years ago. One reason was that in ecology where I work, nothing is ever linear. And these SEM tools rely on the correlation, or what's called covariation matrix. So assumes linearity, unless you add some sort of squared variables in there or do some other trickery. It's not straightforward, at least, to do non-linear regression. So how do you approach that problem?
Oh, okay. I think in that case, you could, there's several ways of addressing that. One of the things I think probably most intuitive is to use your variance covariance matrix and then synthesize them together. If you wanted to go the same way. I mean, ACM style of analysis is that take the variance covariance matrices of each of these individual studies, if you can get them, and then synthesize them together. And so you get a synthesized variance covariance matrix, which you then analyze. That's the one that I didn't cover here. But for non-linear regressions, that would be a preferred way to get these things done. rather than the ones that we are doing here. Here it's more like traditional meta-analysis, two variables taken together and working it out.
Yeah, thank you very much. And also, I remember working with that. It was much more familiar for as you work with mixed models in R. It's just the same sort of coding, and you don't have to know what the latent random effect or random what's it called again? yeah, you don't have to learn the new terminology. It's just a mixed effect model put together.
Yeah.
But yeah.
So basically what happens is this, that in summary then, is your meta-analysis is by nature multi-level. Two-level meta-analysis, random effects meta-analysis is a special instantiation of three-level meta-analysis, and fixed effects meta-analysis is a special case of random effects meta-analysis, like a single level. Yeah. And you can do structural equation modeling for multi-level modeling. So if you combine the two, you get this pathway of structural equation modeling doing meta-analysis. That's all the thing is. I think the real, in my experience, the real attraction of SEM is in multivariate meta-analysis and in enabling me to do what is called meta-analytics structural equation modeling. That is, I take correlation matrices, put them together, and reanalyze them using SEM, which is going to be quite useful for many disciplines such as environmental sciences, ecology, work such as health sciences to some extent, behavioral sciences, and so on and so forth. Medicine benefits a lot from traditional meta-analysis, but these guys are quite different. Ones where they have got particular heterogeneity is an issue. Question in the chat. I need to leave now. Thank you for the wonderful talk. Thank you very much. Please keep in touch. Okay.
So I was also wondering how much this differs from network meta. Now, because a lot of the concepts and the issues it's solving sound similar. Is it just that it has more of a structure you can specify?
Yes. It's more of a structure that you specify to conduct the meta-analysis. Network, of course, is a different. It's a different tool set for doing different things, making multiple comparisons across the board. Well, I don't know the correct answer whether you can use SEM for network meta-analysis. That's something that I will need to study more on this to answer this correctly.
Okay, so I think that's probably all the questions for today. Leaves me just to thank you again for a really cool workshop. I really enjoyed that. And then say thank you for everyone for attending and for watching on YouTube. Oh, sorry, Anders, did you have one more question?
I tried to clap my hands in the reaction.
Okay.
It didn't really work.
That's okay.
But thank you very much.
Great.
Everyone, and we'll see you all tomorrow in the last day. Lots of exciting sessions coming up, and we'll see you then.
Fantastic. Yeah.
Thanks.